All right, I think we are live. So let me just make sure everything is okay in terms of the setting, the screens, the browser tabs and stuff. Okay. Okay, great. All right. So I wonder if anybody could just give me a hint as to whether my voice is audible, whether it's all good. Maybe you could just send a message in the chat box. Because I haven't done this streaming thing for a long time. The last time was actually before the pandemic. So I'm just hoping that, I'm hoping for the best, hoping that it is all going to be okay. So I'm just going to wait for maybe a couple more minutes for people to join. Hopefully they will join. All right. So I can see that there are 2 concurrent viewers at the right now. So if anybody could just, send a message in the chat room or in the chat box and just let me know whether you can hear me properly, you could see me properly. That would be much appreciated. Then I can get started with the talk. All right, I think that probably nobody's there, but anyway. I'm just gonna hope that everybody can hear me fine. So in terms of the content, let me just so we've got 3 people. Okay, great. Oh, thank you very much, Zahra. Really appreciate it. Yeah, because I didn't know what was happening. All right, great. So hopefully more people will join. Because this is, to be honest with you, this is one of those very, very, very important videos that I've ever made in MLDon. And the main reason is because I've met many, many people during my time in machine learning that, who have started their journey in machine learning, but all of a sudden they find themselves overwhelmed by, the possible alternatives out there in terms of, let's say they want to define a research question that they want to, solve. Okay, how to find that research question? Let's say they want to choose a certain algorithm, machine learning algorithm to actually start their journey with. Again, they find this big annoying question that, okay, like which algorithm am I going to use? Am I going to use a decision tree, a support vector machine, an artificial neural network? And if, for example, in an artificial neural network, am I going to use, an autoencoder, a multi-layer perceptron, or an LSTM, and so on and so forth, right? Where to find data, right? What kind of pre-processing is needed for the data? How to set up the experiment in terms of, should I use hyperparameters, how to tune the hyperparameters, how to set up the experiment in terms of, I'm going to need training set, validation set, test set. So anyway, all of these questions for someone who has just started with machine learning could be really overwhelming and at times scary, okay? I've been there, right? Trust me, I have been there. When I started my journey in machine learning, trust me, I did not know what Keras was, what scikit-learn was. I had never written one code in Python, never did PyTorch before. I had never done any TensorFlow coding. I didn't know what pandas was, what NumPy was. I didn't know any of these things, right? So I can totally understand that. I can totally relate to that. So if you feel that way, whether you are in the industry or you're in academia and you've just started your journey in machine learning, I strongly recommend you guys to follow me with this in this video, because I think the content would be really useful for all of you out there, okay? And before I get started with the content, please make sure that you would share this video with as many people as you think could benefit from it. Also, make sure that you would like and leave comments. All of these things would actually help YouTube to recommend this live session to more and more people who could benefit from this. Trust me, it's a pain to have all of these questions in front of you, and I'm trying to help out to basically as many people as possible, right? So let's just get started. So let me just grab myself and go to the... grab my screen and go to the corner somewhere around here, maybe. Okay. Then I'm gonna start writing. Right. So let's get started. First things first. Let's say you have found this problem that you're really fascinated with. It could be something about, say, tumor detection in brain MRI images. It could be predicting the grass growth in farms. It could be predicting a certain protein structure given a sequence of amino acids. It could be predicting the stock market. It could be whatever you want it to be, okay? Here's the thing. You might find this really interesting. You might find that problem really attractive. But the one question that you have to be brutally honest with yourself about is this really an interesting problem, right? That is very important. Is it a real important problem, an interesting problem? And if I were to solve it, would anybody care? I know it's a painful question to ask yourself about something that you're passionate about, but unfortunately, you have to ask this yourself, and you have to be the devil's advocate. That's the ugly truth about it. And you also have to ask yourself, has anybody done this before? And that is where this thing called the literature review comes into play, right? So you will do this thing called the literature, I'm going to put lit review, right? So literature review would give you a very good sense of who has done similar things, what kind of approaches have people been using to solve this problem. So after you do a literature review about, say, for example, let's say brain tumor detection, right? You have this beautiful idea and you're really fascinated about it, and you want to see whether people have done something about it. Have people been addressing the same problem ever? And if they have, what kind of methods have they been using to solve that problem, right? So that is where you end up with, let's say you read 10, 20, 30, 50 papers, okay? So you might come up with a sort of conclusion that, okay, in general, the methods that people have been using to solve that problem, for example, I'm just thinking out loud here, okay? So let's say they've used deep learning approaches and, say, kernel-based approaches, like SVM-based approaches, right? So, or, I mean, you could add more. You could have, like, tree-based approaches, like random forest, like decision trees, and so on and so forth, right? That's my point. After you do a literature review, you understand, okay, this problem, look, this is interesting. People have been trying to solve it. That's number one. You understand that that's important. Number two, you realize that, okay, in general, these are the methods that people have been using to solve this problem. So it gives you a nice structure of what people have been doing. This could help you, basically, this could prevent you from reinventing the wheel. And that's something that you hear a lot, right? You do not want to reinvent the wheel. That's very important. So you don't want to spend months and months on implementing some algorithm and then doing many experiments, spend sleepless nights worrying about the outcome of the algorithm, only to realize that people have done similar experiments gazillion number of times. That's a very ugly outcome, okay? So you want to prevent that. So literature review is very, very important. So let's say you did literature review and you realize that, hey, this problem is interesting. And hey, this is how people have been trying to solve this problem. So usually in those papers, there's a section where they actually describe some sort of a future work or some sort of a research gap that they're trying to solve. My point is you have to be absolutely critical while you're reading those papers, because you want to figure out what is missing from the literature as well, right? So where is that research gap that I could potentially tackle? And that would be your edge. That would be your selling point, right? Because then you realize, okay, first of all, this problem is important. Second of all, people have been trying to solve it using these methods, these categories of methods. Third point, the most important point, this research gap exists across everything that I've seen, right? So all of a sudden you have a selling point. Then you can decide how to tackle it, which we're going to get to later on. Now, let's say you've got this problem and you figure out it's important, it's an interesting problem, and you found the research gap. Then the next question is, let me go down below. Then the next question is, do we have data? So after you do literature review, then the next question is, do you have data? Right? Do we have data? Right? This is, I mean, I've seen many people who have started their PhD experience or who have joined industry projects, but they've only found themselves in this annoying state of, hey, we don't have any data, right? So that's really annoying. So when you find this interesting problem at the same time, and when you're reading those papers, make sure that you would actually answer this question. Like, do we have access to a data that could actually, help me solve this problem, right? And then the question is, okay, where should I find this data, right? Let's say you don't have data, or let's say you want to just search for whether there are different types of data that could be handy for this particular scenario, this research gap that you want to tackle. There are different repositories out there that have been designed for example, like let's say especially machine learning experts to actually find data sets in, right? I'm just going to show you a few of them that are really interesting. So the first source that I'd like to tell you about is Kaggle, kaggle.com. It's a beautiful website. You have competitions out there, like people put up data sets there, define some scenario like classification, like regression, like time series forecast, and then they create this competition and see who would win, right? They have codes, they have discussion forums, and they also have data sets. So if you click on data sets, there you go. I mean, you could define which area you're looking for: computer vision, NLP, data visualization. You could filter your search, or you could actually devote a data set to the platform. You could dedicate one. So here you can, I don't know, search for, let's say, brain MRI, right? So I search for it, and all of a sudden, you've got all of these data sets at your disposal. 94 data sets, and you click, say, on the first one. So this is a brain MRI segmentation task, right? Let's say that's the type of problem that you want to solve, right? And you found that research gap in detecting, in say, segmentation of, medical images. So all of a sudden you find this beautiful data set. And you can read the description of the data set. You can see, okay, how many brain images are available. You've got like 110 directories. I presume in each one of them you would have some sort of a file. So unable to show, because I mean probably the extension of the files are not. Those are TIFF images, right? So they don't have the proper viewer here. But that's the point. So the size is 1.6 gigabytes, right? 1.06. And the other interesting part here is that I'd like to draw your attention to is, if you go in code, you'd find people who have tried to solve brain image segmentation. And I mean, you can see like many people have submitted codes here. Let's say I'm just going to open the first one, and you all of a sudden you see these notebooks, right? Python, I presume, yeah, Python notebooks. They have left comments. They have explanations. Some of them are good, like some of them are really well documented, but some of them are poor, right? So this is just a random example. So you see the code, how they read the images, they have visualized these images. You can see the code. They've used CV2 here to visualize the images, and so on and so forth. Defining loss functions. Here they've defined an artificial neural network, I presume. Yeah. And yeah, this is their neural network, and I think somewhere down the road they have to have, yeah, this is the training process, right? Epoch 22, epoch 23, and the training and validation errors, and at the end evaluation, and here's the actual segmentation happening. So this would give you a beautiful starting point, right? So it's not like in the old days where you don't have access to any data anymore. Right, so you have a huge variety of data sets at your disposal, and that's great. Okay, so that's one website, Kaggle.com, that you could use. The other website that's very famous is called the UCI dataset. So here you could find, God, I mean, it's a potentially limitless number of data sets. So you could find data with, I mean, in all sorts of, what is it? All sorts of data sets. For example, if let's just click on Iris. This Iris is a very well-known data set about flowers. You could actually search. I presume I should be able to search here. Let's say brain, or yeah, brain MRI. Okay, so it just took me out for some reason, but anyway, yeah. So you see that you have, again, brain MRI images. You have descriptions of those data sets, how many attributes you have. So here you can see that this one is really nice, right? So you can see that, look, it is for classification, it has missing values, number of attributes, number of instances. So it's a pretty small data set, right? So UCI is, I mean, you find data sets that are not that large in size, unfortunately, but it is what it is. It's better than nothing. So something like this wouldn't be ideal for training a deep neural network, let's say. Okay? Now, UCI is one other example. The other one that I'm a big fan of is PhysioNet. So using machine learning in medical applications has become really such a hot topic, to be honest with you. And people are actively looking for data sets. Oh, I can actually see Zahra. Zahra says, okay, Zahra is the Kaggle master. I applaud your confidence, your self-confidence. That's great. And yeah, thanks a lot. Diptasri, if I'm pronouncing your name right. Great initiative. Looking forward to it. That's great. Thanks for your support, folks. Yeah, so PhysioNet, right? So this is an amazing, amazing repository. And it's full of all sorts of, data that you could dream about. Some of them are like open. You can just use them however you want. But let me just click on this first ECG database. Right, so this is where I want to draw your attention towards one very important factor. So when you're looking for data, you have to ask yourself, first of all, is there data available for me, right? Second of all, is it publicly accessible? Also, you have to check whether the creators of that data set, have stipulated some sort of a condition for you to be able to be allowed to use that data set, right? For example, here, if you notice, they're saying that when using this resource, please cite the original publication. So you gotta make sure that you cite the data set the way that they're asking you to do that, right? Also here, they're saying that please include the standard citation for PhysioNet, right? There are times where you have to actually, take a course. I'm not kidding you. That happens. So you have to take the course in order to be given the license to actually use that data set. So my point is, regardless of the data set or the website or repository that you're checking out, make sure that you would read the corresponding web page for that data set in and out to make sure that you are using it the way you're supposed to be using it, right? Because otherwise, you don't want to have some sort of plagiarism, lawsuit on your case, saying that, okay, they're using the data set not in the manners that they were supposed to, or they're using a data set that they were not allowed to use, for example, for financial purposes. Sometimes the data creators say that, look, you can only use this for research purposes, but not in a sort of a project where any of the parties would benefit some financial gain, right? So that is why I'm saying you have to make sure you read those websites really clearly. By the way, folks, if you have any questions, feel free to post them in the chat box. I have the chat box in front of me, so I can just follow on the questions. In the meantime, I'm gonna move on. So we talked about the data sets and sort of how to find them, right? One more source. This is the UCR data set. I found in my days that, when I started my PhD, I struggled a lot to find data sets for time series, right? So this is the UCR data set, and it's all about time series data for classification purposes, of course. So this is one more resource that I wanted to share with you. Well, it's interesting that saying that it's discontinued. There is now a larger archive here. Okay. Even a better looking archive, I have to say. I think the person behind this repository is Eamon Keogh, one of the prominent figures of machine learning. I think it's Eamon Keogh. Yes, Eamon here. Eamon Keogh is here. Yes. So I think, he was one of the main guys behind creating this repository. So I was right. So this is another resource. That's my point, right? So at this point, let's say you have found the problem. It is interesting, and you've done your literature review, and you know that the data is available, and you know the conditions under which you are allowed to use that data set, right? That's great. Now, here's the thing. You have started your journey in machine learning, right? You're excited about machine learning, right? But here's another ugly truth. You have to ask yourself, do I need machine learning to solve this problem? This is a question that many people wouldn't ask because they don't want to know the answer. And rightfully so. It is not an answer that, people would look forward to hearing, because sometimes there are problems that look interesting, and they are interesting, but you do not necessarily need a machine learning algorithm to solve those problems, if that makes sense. Sometimes using some sort of a statistical technique would suffice, right? So sometimes, let's say you're looking for, you have this problem of, defining anomalous temperatures in a room, right? You've got sensory readings about the temperatures of the room. You found a data set, and let's say, I'm just going to simplify this for the sake of the argument. Let's say you've got temperatures that are related to whether there is an anomalous sort of temperature in the room, or everything is okay. We have room temperature and nothing's going wrong. There is no fire anywhere, let's say, right? So in that case, in your data set, you could say that you have, let me say, well, in your data set, you've got two types of data. One is related to like very high temperatures, while the other is related to cool and low temperatures, right? So all of a sudden, you look at this data set, okay, it is interesting, it is align with the problem I'm trying to solve. And look, we have two types of data. So we have two classes of data. And then you say, okay, this is a classic data set for binary classification. And look, we have all of these binary classifiers in machine learning. So let's just implement a binary classifier. And you just jump into, implementing it and doing experiments and so on and so forth. However, if you had taken the time to actually visualize this data, right? Some sort of a, maybe like a bar chart. Let's say you could use a bar chart to look at the distribution of this data, right? So if you were to actually look at, say, here you have the temperatures, which are the actual values within your data set, and here you've got the frequency, right? If you had taken the time to actually study the data a little bit, you might have been shocked to know that, look, there are huge number of temperatures around, say, let's say 27, we have here 26, 28, let's say, and we have here values like what? Say, I don't know, 50, right? 50 degrees. And if you were to look at the distribution of your data, you might have seen the case that, okay, where's a huge presence across these values. And again, there's a huge presence across these values. And you can clearly see that there is a nice decision boundary between the two, right? This is the nice decision boundary, say at 30 degrees, for example, right? Let's say this is at 30 degrees or 35 or 40, right? So all of a sudden you can see that, okay, look, without any machine learning, I can actually look at the data, and this threshold will do the job. This threshold can tell me whether I'm in the red zone or blue zone. So you have your binary classifier with just defining a threshold using visualization. That's it. You don't need machine learning to solve this. That's the type of scenario I'm trying to draw your attention to. So my point is, regardless of how interesting the problem is, and how, and also regardless of the fact that you have data to solve that scenario, to solve that problem, make sure that you have a good case of using machine learning to solve it. That's very important. Now, let's say you ask that question and you realize that, look, I do need machine learning to solve it, right? So you now at this stage, you can say that I need machine learning to solve this. I need machine learning to solve it, right? This is a good place to be, by the way. This is a very good place to be. Now, what's the next step? The next step that I would strongly, thank you very much, Sahra. Thanks a lot. I just read your message. So the next thing on the list is you need to, as you might have guessed by now, you have to get comfortable with your data, right? Let me tell you what I mean by that. You need to make sure that, let me erase these. Right. When you look at your data, right? So let's say you've got your data set here. Right? Beautiful data set. You're excited about it and everything. But before you start touching that bloody keyboard, before you start thinking about models, first things first, get comfortable with your data. As Gordon Ramsay says, get comfortable with the fish, get comfortable with your knife. It's the same story. Get comfortable with your data. You have to be able to maybe, through different methods, statistical methods. You could use statistical methods. You could use visualizations, or yeah, I think these two are pretty much capture the whole thing. You could use these things to answer certain questions. And what are those questions? Number one, do I have missing values? Missing values. And if I do, what percentage of the data has missing values? That's very important. Now, and by the way, if I have missing values, what am I going to do about them? Am I going to throw them away, those data points? Am I going to somehow find a method of, what is it? To estimate the value of those missing values. Some sort of averaging technique between the neighboring points or whatever, right? So you have to make sure that you're clear about what you're going to do. Because you might already not have enough data, and getting rid of missing data points with missing values might not be the best strategy, right? So give it a little bit of thinking and then decide accordingly. Thanks a lot, Jimbo. You're really kind. Right. Number two, do I have outliers? Outliers, right? So outlier, let me show you here. So one of the things that visualizations would help you with is, for example, let's say you've used a box plot, right? So these guys are the outliers. So for example, with this particular, on Thursdays, you are, recording total bill of something. And you notice that these data points, as far as this visualization is concerned, are the outliers, meaning that they're out of distribution. So if you have outliers, what's the percentage of those outliers, right? And what are you going to do about them? Are you going to get rid of them? And also, you got to make sure that they're actually outliers, right? So this is where you could actually talk to a domain expert and ask them, okay, look, this visualization is telling me that total bill of around 40, 50 is unrealistic, and it can't really, it can't be counted as an inlier. Is that really the case from your domain expertise? And they might say, no, actually, it's very common. Your data just happens to be fully biased towards values between, so for example, here around 10 and between, say, 10 and 30. So it means that your data set is not a good representative of the truth out there. Yes? So that was the other point, finding outliers. Now, and yeah, using visualizations, right? There's all sorts of visualizations that you could use. You could use histogram, you could use box plots, you could generate an actual, distribution plot where you could see, where the data is biased towards, and these are really informative. And the other thing is, so you could actually use some statistics from the data, right? Look at the mean. Look at the variance. Look at the median. Maybe even mode, the mode of your data. All of these would actually help you, get comfortable with your data. There's a nice question in the chat box. Zahra is asking, what's different between outlier and noise? That's a great question. Now, noise, let's put it this way. A noise is an outlier, but not every outlier is a noise. If that makes sense. Let me say it again. Every noise, say noisy data point, is an outlier, but not every outlier is a noisy data point. Because outliers might be informative, right? So, and let me put it this way. So if you were to visualize your data, right? Say you're visualizing the case, let's say the height and the weights of different people, right? So let's say you're just visualizing them and you realize that, okay, most of the people are falling in this region in your data set. And you might find a couple examples here, right? Let's say you've got, I don't know, 500 people here, right? And you've got only 2 people here that seem to be outliers, seem to be out of distributions, right? So only 2. Question: are these truly outliers? Now that's important. They might be, right? But it might be the case that your dataset is simply not a good representative of your community. It might be the case that there are, if you had a better dataset that is a better representative sort of a set of the actual community of the people, it might be the case that you would have had, maybe I should choose a better color. Hopefully this would, maybe you would have values like this, right? You see the yellow bit, but you just happen to not have those measurements of those people, right? So if you were to see the whole picture, you would have said, okay, those 2 people are not outliers. I just happen to not have enough data from that part of the community, from that part of my population, right? So again, that's why you could talk to a domain expert and they might say, okay, people with this sort of height and this sort of weight, it's common. It's common amongst teenagers, for example, right? Or maybe in this part of Europe or Middle East, right? So it's very important to make sure that if you're determining that something is an outlier, it truly is an outlier, right? So be careful about that. I hope that I answered the question, Zahra. Let me just take a sip of I've got this ML Dawn mug, customized. Great. So next thing on the list is, yes. Okay, great, Zahra. Happy it was helpful. Now, next thing on the list is, you've got your data, you know you're going to use machine learning, you've got comfortable with your data. Next thing is, you need to, actually, before I move to the next item, one other thing that is very important is, maybe I should mention it here actually. Let's say you're dealing with a classification task, right? And you look at the number of examples, the number of data points per class. It might be the case that you might have a huge amount of what we call imbalancedness. Let's say you're looking at, brain tumor images, right? And let's say your population is like, I don't know, the size of your data set is like 1 million people, right? Brain MRI images. Now, let's say you have 2 classes, healthy and tumor. But when you're in the middle of getting comfortable with your data, you realize that, wait a second, I've got 98% of the images belong to the healthy class, and 2% belong to the tumor class. So all of a sudden you've got this huge amount of imbalancedness between your 2 classes. This changes everything. So if you were to use a binary classifier like, I don't know, like a neural network with 2 neurons in its final layer, or if you were to use a decision tree or whatever model have you, a SVM, all of a sudden you have this huge amount of imbalances in your data, meaning that you want to build a binary classifier, yes. However, you don't have enough amount of representative data points for each one of these classes. So you have a lot to say about the healthy class to your machine learning algorithm, but you don't have enough examples from the tumor class. So you don't have enough, your algorithm will not fully understand what it means to have a tumor in a brain MRI image, if that makes sense. because of that, the decision boundary that this algorithm is going to learn between these two classes is gonna be really inaccurate. Like, really inaccurate. So all of a sudden, like, I mean, what I'm talking about is like this, right? So let's say if I were to visualize this, let's say I had a way of visualizing this in 2D, right? So let's say you've got a lot of maybe a little bit of tumorous images, and you have a lot of healthy images. A lot, right? So all of these, like thousands and thousands, right? Now, you've got 98% for healthy images and 2% for tumor images, right? Here's the problem. You look at this and say, okay, this is terrible. But, I mean, let's say you find a way to actually create a binary classifier. I'm going to tell you how, but let's say you found a way, right? Here's the problem. If you had the chance to actually lay your hands on more examples of this minority class here, this 2%, you might have observed the case that, okay, you've got images that are here. Actually, huge amount of overlap between the two classes, right? So, because you don't have enough number of examples from the minority class, the decision boundary that your classifier is bound to learn is going to look something like this. It's going to look something like this. And remember, this is a decision boundary that your algorithm has learned during training. Yeah. Now, during testing, during inference, a new example might come in that happens around here. This is test, right? And let me choose a different color. This is another some example happens here, some example happens here, some happens here, some happen here. And your algorithm will label all of them as healthy because they're on this side of the decision boundary. But if you were to actually look at the truth about them, they might all belong to the minority class. They must all be tumorous. Now, the cost of labeling someone who has actual tumor in their brain, labeling them as healthy, the cost of this is death. You're telling a patient, look, you're healthy, you're grand, you're fine, go home. But in fact, they have a tumor. So you notice that this decision boundary is worthless. Very, very dangerous. Right? Especially if it's a healthcare application, right? So you have to make sure that you figure out the imbalancedness in your data. And then the question is, if you have huge amount of imbalancedness, what are you going to do? So that's very important. There are many techniques to overcome imbalances and different methods. One of them is like you could actually use upsampling techniques. So you actually upsample the minority class. One of the very famous ones, actually someone asked this question on Facebook today. One of the very famous ones is called SMOT or SMOT. I don't know how they pronounce this. So it's a technique to actually upsample the minority class to make sure that it will come to a decent number compared to the majority class, right? So yeah, the other approach is the other approach is basically you're not going to care about the imbalances because you're not going to create a binary classifier. What you're going to create is going to be a anomaly detector or a one class classifier. So this family of classifiers is actually has been built for anomaly detection for the exact same problem that you have here. So these are the sort of techniques that are you can actually train them with, say, all the healthy images, right? You don't probably even need to have the 2% is actually enough. You train them with all these healthy images, so they will learn the distribution of healthy images, right? And then what happens is, after learning it, during inference, when something comes along, like some sort of tumorous brain image that falls out of that distribution, they would flag them as anomalous or weird, right? Out of distribution. And just to give you an idea, most of the algorithms that you know out there, they have some brother or sister algorithm that has been sort of designed for anomaly detection. So if you have SVMs for classification or regression, you have one class SVMs designed for this particular task, or you have SVDD, support vector data description. So if you have random forests or decision trees for one class classification, you have isolation forests. What else? When you have multilayer perceptrons for classification, you have autoencoders, which is a family of neural networks that can be used for anomaly detection. So it's with autoencoder is really funny. It actually, you train the autoencoder with the instances of one class, and it learns how to reconstruct your majority class samples. And if it fails to reconstruct a given example during test time, so it would fail miserably, right? It can't reconstruct it. So the reconstruction error would just go really high. And that is how it actually tells you that, okay, I believe this particular input data is weird because I failed to reconstruct it, right? So it's a very interesting usage of autoencoders for anomaly detection. But I digress. Right. I just want to talk to you about the imbalances as well. So this is all about getting comfortable with your data, okay? Let me get rid of these as well. Clear the board for the next item. Let me take a look at the comments. If our model detection, everyone, is healthy, our accuracy is 98%. Yeah, that's a good point. I'm going to actually get into the evaluation metrics where, you know, that's a very good point, where accuracy is a terrible evaluation metric when you have imbalanced data sets. Well done, Zahra. I will talk about this actually. I was actually planning to talk about this very thing, to be honest with you. Are you reading my mind or something? Okay. Right. The next thing. So let's say you've got comfortable with your data. The next thing is define your task very, very clearly. Are you going to do classification? If you're going to do classification, is it going to be a multi-label classification where an input data could belong to, multiple classes at the same time? Is it going to be a multi-class classification where an input data can belong to one class at a time? Is it one class classification where you're actually developing anomaly detectors? Is it regression? Is it time series forecast? Is it clustering? Is it supervised learning? Is it semi-supervised learning, which is totally dictated, by the way, by the ground truth labels you have, right? Is it semi-supervised? Is it unsupervised? Is it going to be reinforcement learning altogether, a total different animal, right? So make sure that you define your task really clearly, right? Be the devil's advocate. Let me move. Yeah, that's about it. Yeah, I think I mentioned everything about that part of the story. Now, here's the annoying part, right? This is one of the most overwhelming questions that anybody new in machine learning would ask themselves. And it's this: what kind of machine learning algorithm should I use? I have the data, I know what I'm going to do, for example, classification. I've taken care of imbalancedness, missing values, outliers. But listen, I've got all of these algorithms out there. What the hell am I going to do? And all of them can do regression or classification or whatever task it is that I want to do, right? Now, I want to tell you about this fundamental, this very important principle in machine learning. And that is called the I hope that I will spell this right. Occam's razor. I hope that I've spelled this right. Otherwise, it would be really embarrassing. So Occam's razor, it actually says that, listen, if you have multiple models, right? And by model, you can think about your model as your machine learning algorithm. Let's say you have model 1, you have model 2, and you have model 3, right? And you're going to use these 3 models to solve a given problem, right? So all of them would tackle the problem. And all of them would generate solutions with decent amount of accuracy, right? So more or less, you're happy, right? So the question is, which one to choose? Occam's razor says that if you have multiple models that can solve the task at hand with a reasonable and acceptable performance, level, choose the model that is the simplest. So simplest in terms of the number of parameters, for example. So choose the model. Let's say these are neural networks. This one has 40 weights, 40 trainable weights in it. This one has 40,000, and this one has 40 million. So you're going to be using this model. You're going to be choosing that model. First of all, because you've seen that this model is doing the job. That's the most obvious answer. But second of all, this model is doing the job with less amount of computational demand, right? So it would be much easier to deploy this model. It is scalable and it's doing the job better in terms of computation, right? The other thing, that sort of hidden reason for choosing a simpler model is this idea of not overfitting your data, right? So you always have this sort of tricky boundary between developing models that overfit your data or underfit your data, or they're a good fit to your data. If your model is too complicated, and when I say too complicated, it means that it is more complicated and sophisticated and powerful compared to the difficulty of the task at hand. So if your data set is actually far too simple for a model with 14 million parameters, what happens is your model would eventually, if say you're not doing, let's say, any regularization or anything, your model could actually overfit your data, right? Then what it means is it would fail to generalize its knowledge to the unseen data because it will end up having memorized your training data. Now, if on the other hand, your model is far too simple for the task at hand, let's say your data set is really sophisticated, right? Little nuances between data samples from different classes, right? In that case, if you're using a simple model, like the same example, the 40 parameter neural network, what happens is your model might actually underfit your data, meaning that it wouldn't even do good on your training set, right? Let alone the test set. It can't even, so the error on your training set wouldn't go down because it just doesn't have the representative power to describe your training data, right? What you want is you want to have a model that would fall somewhere around here, the good fit. We're going to be talking about this, by the way. One of the things that would actually dictate the complexity of a model, the representativeness of a model, is actually the hyperparameters that basically effectively indirectly they are controlling the number of parameters in your network. But I digress now. I don't want to get into it, but the question was what model to use, right? And Occam's razor says use the simplest model possible that gives you the highest performance. right? So that would be your sort of trade-off. Now, usually, in these sorts of experiments, what people do is actually they create a benchmark experiment. So whether you're doing your research as an academic in machine learning or in the industry, this is something that you need to do. You have to create a benchmark, and when I say have to, I mean have to. Benchmark experiment. You need to have a variety of families of machine learning algorithms here. You should have things like, I don't know, decision trees. You should have artificial neural nets. You should have nearest neighbor methods, like k-nearest neighbor, something as simple as that. You should have what else? Kernel-based methods, and so on and so forth. And you notice that there's a reason why I've chosen, mutually exclusive sort of families of algorithms, and it's because there was this paper, I actually forget the name, in recommendations, in the area of recommendation systems. And what they had done was, this is amazing, they had selected a handful of papers from the recommendation system journals, some of the best algorithms ever. They all happen to be sort of deep learning based approaches, by the way. What they did was they actually beat those sophisticated algorithms for the most part with nearest neighbor based families. These guys, with simple k-nearest neighbor algorithms, they beat them. Right? So that is why I'm saying you have to have a benchmark of different techniques to actually try and solve the problem. And Zahra just mentioned that, clustering. Yeah, clustering would be clustering based, like k-means clustering, right? Would be another family. So there is this thing called the inductive bias that sort of, describes the logic and nature of the problem at hand. Certain algorithms' logic would align better with the inductive bias of your task compared to other algorithms. For example, when you're dealing with a computer vision task, having a convolutional neural network is far more suitable compared to using a multi-layer perceptron, because the inductive bias of a computer vision task really aligns well with having convolutional filters that actually consider the spatial dependencies amongst neighboring pixels. Because the inductive bias is there is a spatial dependency amongst neighboring pixels. So because that inductive bias is there, having a neural network that can actually use convolutional filters would be really satisfying and would really, be appropriate for the task at hand, right? So make sure you create a benchmark of algorithms that are reasonably different from one another, right? So effectively what you'll end up doing, by the way, I'm actually walking you through how to design your experiment, right? So let's not forget that. We are on the same path. So you will end up with some sort of a table of, like that, right? Here you have your, you have your MLP, multi-layer perceptrons, you have your convolutional neural networks, you have your k-nearest neighbor, you have your SVM models, you have your one-class SVM models, you have your k-nearest, let's say k-means, so on and so forth, right? And usually the vertical side would be the scenarios that you're going to be defining in your data set, right? So this could be one scenario where you are putting class 1 against class 2, for example, for classification. Let's say you have 10 classes in your data set. Next, you're going to try and develop a 1 versus all sort of scenario, right? This is the case for, like, you can use this, so, like, can I create a machine learning algorithm that can discern between examples of this particular class and everything else, and so on and so forth. So each column will be a given scenario, right? Scenario, and that you'll be trying to solve. right? So I haven't still talked about the actual, experiment setup in terms of the evaluation metric and so on, and so on. But this is just the big picture, right? So this is what you need to do. Choose a variety of algorithms that are really simple all the way to sophisticated algorithms. That would give you a great picture about what sort of algorithm would align well with the inductive bias within your data. Okay? Great. Right. I think I talked about everything I want to talk about. And now I'm going to jump into experiment setup. Before I continue, please, just going to remind you guys, please do share this video. I mean, I would love for people to actually join while we're having this live session, because you see, these problems, actually this could be also a little bit of a break for you guys as well. Let me come somewhere in the middle here. You see, these questions are really, really critical. I found many PhD students who have felt really, overwhelmed, who've been overwhelmed by where to start, right? So for you to actually share this video, especially while we're in live session, where people could actually join and they could actually, ask questions, and we all could discuss these questions together, could be really helpful for many people in their research. So please, I would really appreciate it if you could, first of all, share in as many groups as possible, because we're getting into the experiment setup. This is a very important part of the whole explanation. And also, if you like the video, YouTube would, the YouTube algorithm, the overlord YouTube algorithm would actually, share this video and show this video to more people around the world, right? So, if there are any questions, post them in the comment section. And while you guys might be thinking about your question, I'm just gonna bring myself up all the way to the corner again. Here maybe. Right. So if there are no questions, I'm gonna continue with the exciting discussion on experiment setup. Now, this is the devil. This is the devil. Now, there are questions you need to ask about yourself. For example, what kind of hyperparameters am I going to be looking at? Now, this is very important. I'm going to maybe show you exactly what I mean. Let's say you want to implement an SVM model, support vector machine, right? So I'm going to actually go support vector machine. So one of the very well-known libraries out there is called scikit-learn, right? And scikit-learn, they have implemented many of these nice algorithms for you to just use, right? So if I go to scikit-learn's page, right? This is support vector machine. They have nice explanation, classification, how you could use it. You have actual code example, like you could actually define your SVM and then you literally fit it to your data, and then you could actually make predictions for new data, and that's amazing, right? So this is for multi-class classification. So everything you need to know is there for regression, right? Now, if I actually go to the actual code, so this is the signature of the function, right? This is where the constructor of the function would ask you to pass, right? To pass to it. Now, I said the question was, what hyperparameters am I going to be using, right? So let's say you want to use SVM. If you look at the documentation on SVM, let's say you want to use the scikit-learn implementation. All of a sudden you realize, whoa. You have kernel. You can define the kernel. You know how we say in SVM models, you have this kernel trick. It is what it is. So here, you could use linear kernel, you could have poly, you could have radial basis function kernel, sigmoid, and pre-computed. Depending on which kernel you use, the performance could be day and night different, right? So which one of them am I going to be using? This is where the literature review that you did at the very top would really come to your help, to your aid, because you see how people have been actually trying to solve this problem, right? Then you could ask, like, for example, here you have this gamma sort of hyperparameter that is called the kernel coefficient for RBF, poly, and sigmoid. What else? I think, yeah, I mean, yeah, I don't want to like go into too much detail, but like you got decision function shape. That's again one important factor that you need to consider with SVM models. But this is just one example, right? The same story goes with decision trees or with, say, neural networks, right? So when you define an artificial neural network, one of the hyperparameters that you need to consider is how many layers am I going to have? It's always a question. People always ask me, okay, how many convolutional layers, right? For each layer, how many neurons do I need to have? For a convolutional layer, how many filters do I need to have? In terms of learning rates, what kind of learning rate should I have? Right? These are all hyperparameters that you need to think about. Some of the lesser known hyperparameters that might not jump at you right from the beginning is, what kind of optimizer am I going to be using? Say, am I going to use Adam? Am I going to use RMS prop, rprop, Nestrov, right? So all of these questions, they're all related to hyperparameters. And to be honest with you, the painful answer is there is no one clear-cut answer to these questions. Usually in the machine learning community, the job is to play with these values and just do this hyperparameter search, right? Now, the search bit could be, you could do the search in different ways, right? Let's say you're thinking about learning rate, right? The learning rate, they usually show learning rate with eta, right? Let's say you want to consider learning rates as small as 10 to the power minus 6, all the way to as big as 10 to the power minus 2. So 1/millionth to 100th, right? Just to avoid confusion, this is not a subtraction or anything. This is just a range, right? But then the question is, we have infinite number of values between these two. And this is your hyperparameter. You want to fine-tune this. You want to find the best value for this hyperparameter that could help you with, say, developing a binary classifier for brain tumor detection, right? There are different methods that you could search this space. One approach that, funny enough, is really strong is random. This is amazing. By simply picking random values, they have shown that you could actually reach reasonable performances, right? The other approach that is very famous is grid-based, right? So what it means is they grab this hyperparameter, they grab the entire range of this hyperparameter, right? So this is, let's say, this is my range, right? It goes from 10 to the power minus 6 to 10 to the power minus 2, right? So what they do is they say, okay, I'm gonna break this into 1, 2, 3, 4 values, or 4 sections. So, and I'm gonna consider the increment something like maybe 10 to the power, maybe 1 by 1, minus 5, 10 to the power 4, 10 to the power 3, and then eventually 10 to the power minus 2, right? I'm going to be trying out 1, 2, 3, 4, and 5 different learning rates. And then I'm going to choose the best one. This is called grid-based. And as you might have noticed, it could be really expensive. Why? Let's say you've got these hyperparameters. You've got this convolutional neural network, right? CNN. Let's think about the hyperparameters that you could have. Am I going to be using, let's say, mean squared error or cross entropy? Error function. So error function is one hyperparameter. The learning rate is another one. The optimizer I'm going to be using. The number of layers that I'm going to be having. The number of filters that I'm going to be having for each layer. I mean, by the way, you could ask this per each layer, how many filters am I going to have? The size of those filters. Filter size, right? So the amount by which you would stride these filters along your input data. So the stride with like that. A filter is like a sort of sliding window. You could think about it, right? So the amount of stride is another one, another hyperparameter. Now imagine, let's say, so here you have 2 possibilities. Here you have, say, in our example, you have 5 possibilities. Here, let's say you chose Adam, you're between Adam and RMS prop. So 2 possibilities. Let's say you're going to try 5, 10, 15 layers. So 3 possibilities. Let's say here again you have 3 possibilities, 3 and 3, right? So how many total possibilities do you have for in your hyperparameter space that you would be searching in a grid-wise fashion? It would be 3 times 3 times 3 times 3 times 2 times 5 times 2 number of combinations. This is ridiculous, okay? So my point is, grid-based approaches, if you have a small hyperparameter space, might be a good idea, but if you have a huge hyperparameter space, might not be the best and, let's say, practical strategy, right? Which brings me to the last sort of well-known method of finding hyperparameters. And this is sort of a search-based optimization technique. There are different ways of doing it. You could use genetic algorithm to try different, combinations of hyperparameters. You could use, like you've got Kalman filters that people have been using Kalman filters to actually search the hyperparameter space for better combinations of hyperparameters, right? So instead of blindly just going through all combinations of your hyperparameters, what you do is you actually you turn this into an optimization technique, optimization problem, where you might go through, maybe you might change your learning rate a little bit and then go and add a couple more layers and then change your number of filters from 5 to 10 and then realize, okay, to change from 5 to 10 seems to be a good idea. How about I keep everything else the same, but increase just the number of filters now from 10 to 15. Oh, got better. 15 to 20. Oh, got worse. Let's go back to 15. But let's go and change the number of layers. So there's a smart sort of searching mechanism that through an optimization task, you could, it could assist you with your hyperparameter tuning. By the way, I just realized that my picture is blocking this bit of this bit of the writing. My apologies for that. What I've written there is called the Kalman filter, right? Let me just get rid of these. So this is, by the way, one part of your experimental setup, right? Experiment setup. Let me put it in the middle. Experiment setup, right? So the first question was hyperparameters. define them, figure out how you're going to actually search the hyperparameter space, how you're going to fine-tune those hyperparameters. Okay. The other thing is, especially, by the way, when if you're going to train an artificial neural network, one of the questions is, actually, let me, I just realized that I need to put myself up here because I keep blocking. Sorry. I'm not an experienced streamer. Okay. So yeah, if you're going to be training an artificial neural network, one of the questions that you should be asking yourself is, how many epochs am I going to be training my neural network for, right? Because that determines your convergence and the quality of the network that you're going to be converging to at the end of the day. Okay, so that's another big question. It shouldn't be treated as a hyperparameter, by the way. It's not a characteristic of the architecture of your model. It is just something that needs to be set. Now, the other thing in terms of experimental setup is how you're gonna divide your trainings, your data for training, the training set, the validation set, and the test set. First of all, make sure that you understand this really clearly. You would put your test set in a box, and you would put it in a shelf and close the door, right? So you should not use your test set during training at all, during validation whatsoever. No, you shouldn't be using the statistics of your test set even during your training, right? So if you're going to be normalizing your data, put your test set away. Don't use even the statistics like mean and standard deviation of your test set in your pre-processing of your data, right? So test set is not to be touched or looked at until the actual testing. That's very important. And I have to tell you, 9 out of 10 of machine learning researchers have faced this problem. They've had this algorithm that is just working like a well-oiled machine, is just doing great, 90-something% performance in in the test set, but it happened to me as well, by the way. They've just only realized that the test set had actually leaked into the training set. So they were actually training on a part of the test set, and then during testing they were actually testing on the bit of test set that had already leaked into the training set. Right? So it's like, before I give an exam to a student, I've already shown them the exam questions. And during testing, I'm going to showing them the exact questions that they had been exposed to. And then I'm going to be happy that, okay, the student has really learned well, but the student hasn't learned nothing. Right? So that's very important. Anyway, so you've got your train, validation, and test set, and you've got to ask yourself, like percentage-wise, let's say you're going to be deciding that, okay, I'm going to be using 70% of my data for training, 20% for validation, and 10%, for example, for test set, right? And this is important, and just as a reminder, one of the reasons that you use a validation set is to make sure that you will not fall into the trap of overfitting. Right? Because you'll be hoping that your validation set is some sort of a good representative of the unseen test set. So you'll be using your train and validation set in such a manner, that's just a very ugly axis. Let me use this pen as a ruler. Let's see if this works. Yay! Okay, so let's say you're doing this experiment. God, that was good. This reminds me, I'm going to have a ruler next to me from now on. So let's say you have the number of epochs here, and you're training your neural network, and here you've got the error, right? So using the validation set would help you to detect this. You remember I told you have to ask yourself how many epochs, right? So as you're training on your training set, you might notice that your training error would just keep going down and down and down and down as a function of your epochs, and eventually would converge into a very low value, right? But your validation error might actually go something like this, right? Going down, going down, going down, going down, going down, and then all of a sudden it would just swoop up, right? This point, my friends, this point at which this phenomenon has happened, this sweet spot, this is how you determine how many epochs am I going to be using to train my artificial neural network. This is where the overfitting has happened, right? So this is one of the reasons you use a validation set, to make sure that you're not going to be, apologies for this, to make sure that you won't be overfitting your data, right? The other reason is you could actually use the train and validation combination to fine-tune your hyperparameters. So you would use different combinations of hyperparameters in a sort of, say, cross-validation experiment, and you choose the combination of hyperparameters that performs the best on across your cross-validation, across all of your folds. Let's say you're doing a 10-fold cross-validation, right? So that's another reason that people use a validation set. I'm going to be getting to the test set in a minute, okay? So don't worry. I'll get there. Yes, I've talked about that. Yeah. So let me tell you, in terms of the experiment setup, I'm going to show you an example, right? One of the very super well-known approaches to actually setting up an experiment using train, validation, and test sets is called k-fold cross-validation. You might have heard this by now, by the way. K-fold cross-validation. Right? And the way it works is, let's say you've got your data, and here you're looking at the combination of both train and validation, right? So this is train and validation all together, right? So let's say k is 3, right? Usually they do 10-fold cross-validation, but just for simplicity, I'm just gonna say, look, I'm gonna be dividing my data into 3 folds, right? So it's 3-fold cross-validation, right? So the first round, I'm gonna be training on these 2 folds, right? And I'm gonna be testing, or let's say validating, right? This is the validation set. I'm gonna be validating on this chunk, right? The second time, again, the same data. This time I'm gonna be training on this chunk and this chunk. I'm gonna be validating on this chunk. And as you might have guessed by now, the third bit is, I'm sure you know this by now, but I can't hear you, so I don't know what your answer is, but the last 2 chunks will be used for training, while the first chunk is going to be for validating. So let's say you use a accuracy for performance, like metric, right? So you might get, I don't know, like 90% accuracy here, you might get 80% accuracy here, and you might get 85% of accuracy here, right? And let's say you're using a combination of hyperparameters for a neural network. Let's say you've used eta equals 10 to the power minus 6. You've used 3 layers, 3 convolutional layers, for example, right? So if you take an average of these 3 values, right? So if I were to, I'm just going to be lazy. And this, by the way, this is exactly how they do it, right? So you get 80% plus 90% plus 85%, right? divided by 3. So 85%. So average 85%, right? You'll do the exact same thing for the other combinations of your hyperparameters. Say other learning rate and other number of layers. And eventually you have a list of hyperparameter combination, performance metric. Hyperparameter combination, performance metric. You will choose the hyperparameter combination with the best performance. Let's say this is the one, right? So you've noticed that you determined that the best sort of set of hyperparameters for my neural network for brain tumor detection is where I use a learning rate of 10 to the power minus 6 and I have 3 convolutional layers. What's next? Usually the next step is you create this neural network with these hyperparameters from scratch now, right? Again, from scratch. This time, you train your neural network with these, winner hyperparameters, but this time you train it on the entire training set. There's no validation set anymore. You train on the entire training set, right? And then you test. Maybe I should actually connect it to here. Then you test on that unseen test set and you get a value, let's say 80%. This is what you should report in your academic paper, in your report in the project, in the industry that you're working on. That is what you need to report at the end. That this is how well your model can generalize its knowledge to the unseen data. So this is what a company should expect from your algorithm to do. This is how well it should expect your algorithm to do for the future, where more unseen data will come in, and your algorithm is going to be assisting the professionals in the decision-making process, right? That's important. So you could report the validation, the performance, the average performance in your validations or across folds. You could do that, that's fine. But ultimately, it is the performance on the test set that is the real deal, right? Next thing that I want to talk about is the performance metric. So I kept saying accuracy, but you have to make sure that you'll be using the correct evaluation metric. That's very important. If you use the wrong evaluation metric for a given problem, you could get a false sense of achievement, right? Or a false sense of failure, really. As Zahra actually mentioned in the comments section, well done, by the way, Zahra. That was really perceptive of you. Yet let's say you have a highly imbalanced data set, right? Where you have 90%, say 98% of examples belonging to, again, let's say healthy brain images, and you've got 2% for tumor brain images, right? So this is the imbalancedness of your data. You want to create a binary classifier, and you want to choose an evaluation metric. You'll be asking, should I use F-score, recall, what's the precision? Should I use accuracy? Should I use AUC, which is the area under the ROC curve, for example, AUC of ROC curve, for example, or AUC of the PR, precision recall curve, right? And I just want to show you what happens if you chose the wrong metric. Let's say you have a machine learning algorithm that is absolutely dumb, right? And this algorithm would actually say, look, this is your data, right? If you pass this to your algorithm, this is your algorithm, the model. right? Let's say this guy predicts everything to be healthy. Everybody to be healthy. What happens? You want to measure the accuracy, right? So the formula of accuracy. Let me just make sure that I'm following the exact best practice. Yes. Yeah. So the formula for accuracy is, actually, am I blocking anything? No, thank God. The formula for accuracy is true positive plus true negative. So let me move it here. True positive plus true negative divided by, let me just look at my cheat sheet, just make sure I'm not messing up anything. You see, that's what happens when you're live streaming. I mean, I knew the formulation for accuracy, but you just doubt everything. You just doubt yourself. Just want to make sure you don't mess anything up. So you've got false positive and you've got false negative, right? This is formulation for accuracy. So for this performance where your machine is saying that everybody is healthy, nobody has tumor. If you were to use accuracy to measure the performance of this classifier right now. So let's say the positive class is tumor, right? So let's say, accuracy is, so everybody's tumor, right? So true positive, first of all, we haven't predicted anything to be positive, right? So there is no prediction for positive. So your true positive is 0, right? True negative, I've mentioned like 98% are truly negative, but I've mentioned that the classifier is saying everybody is negative, right? So 98% of them were true, were right? So let's say you have 100 data examples, right? Just to make the calculation easy. Let's say in your data set you have 100 samples. 98 of them literally are healthy. 2 of them happen to be tumor, right? So in that case, the true negative, the ones that the algorithm says they're healthy, and it is true that they're healthy, 98 of them, right? Now, down here, true positive, again, 0. True negative, again, 98. False positive, there is no prediction for positive samples. So again, 0 here. False negative, how many of them have been classified as healthy but mistakenly? 2 of them, right? So we have only 2 false positives, right? So this becomes 98 divided by 100. This becomes 98%. Now, the cost of saying someone is healthy while they have tumor, the cost of that is death, right? So you do mind if your classifier misses a positive case. You really do mind. And whereas the other way around is not that important, because, I mean, it is still important, but not as important. Like if somebody, say, doesn't have tumor and your classifier says, hey, you have tumor. Yeah, I mean, it's terrible. The person will go through trauma, will get depressed, and it's going to be a major shock, right? But it still is not life-threatening, right? So that is the case where, so this classifier, under this scenario, we are getting 98%, right? But it doesn't say what the classifier is exactly doing. It doesn't say how terrible it is. It has actually missed the 2 examples that we had and believes that everybody is healthy. Like if you have a classifier that doesn't learn anything, it just predicts everybody to be healthy, it will do 98% on such data sets. 99, 97%, right? But it's a very, insidious value, insidious performance metric for such scenarios. And as Zahra mentioned in the chat box, yeah, F1 score would be a good performance in these scenarios. That was just one example, okay? So make sure that you would choose your evaluation metric appropriately. That's very important. And we are getting to the last chunk that I want to talk about. So as I said, you've defined a table of algorithms, right? According to Occam's razor. According to Occam's razor, you have simple models, and then you have actually defined more sort of difficult and more complicated algorithms as well, right? So you have a good selection of algorithms, right? And you have reported your test score for each of these algorithms. So at the end of the day, you should have a table of results, right, with algorithms and different scenarios. So I mean, just to give you a simple example, EBFDD. This is just one of my own papers. Hopefully I'll be able to open this. Maybe I won't be able to because I just want to maybe show you the other paper. This one was from a workshop where I published years ago. I just want to give you an idea. When I say a table, for those of you who are new to this is what I'm talking about. It's funny because one time I searched for RBF because this algorithm is called RBFDD, right? I'm going to show you here. Just first let me show you the table of results, and I'm going to share a funny memory. Yeah, so this is the kind of thing you're looking at, right? So let me just zoom in. Hopefully I'm not blocking anything, right? So if I just zoom in, you see, so you have algorithms, one class SVM, autoencoder, RBFDD, and here you have dataset 1, dataset 2, dataset 3, dataset 4, and under each dataset you have different scenarios, like this versus this class versus that. And under each one you have the performance metric. And at the very end, you're sort of taking an average across all of the datasets, all the scenarios for this algorithm, and this would be you're basically taking the average rank here, right? So here in this case, you can actually rank which algorithm did the best for each scenario, and then taking an average of the ranks. With one look, you notice that, okay, for example, here, one class SVM is doing the best, right? So this is what I mean by at the end of all of these experiments, you'll come up with a big giant table, and this is where you can think about the best performing hyperparameters for each data set and for each scenario. Which one is it? You remember I said you can actually choose best hyperparameters based on, say, cross-validation, for example. This is it, right? So you can actually report the best performing hyperparameters. It's actually nice, a good practice. It would help with reproducibility of your paper. It's good practice. Not many people do it, but it's a good practice. So the funny memory is, so this algorithm it's a very basic, very simple algorithm, really. And so it's called the radial basis function data descriptor, RBFDD. I remember the first time I Googled RBF on Google, what came up first, it wasn't radial basis function neural network, it was actually resting bitch face. And there was this these faces of these women with like the resting bitch mode, like they're looking at you and they're very like, I'm gonna kill you right now. And that was really funny. I was expecting RBF algorithms, but I got resting bitch face. We laughed a lot. Right. I'm just gonna give you two last pointers. Like, these two last points are not like critical, right? But they're good. They're good things to have in your report or in your paper. God knows, like, how many times reviewers have gotten back to me complaining about not having these particular 2 points, right? I'm just gonna let you know what they are. First of all, you look at your table of results and you see that, okay, if this algorithm did better in these scenarios and that algorithm did better in those scenarios. You have to, not have to, but it would be good if you could actually, so when you have your results, your table of results, right? So let's say these are your results. It would be good that if you could create some sort of, generate some insight as to why a given algorithm was doing better, on which data set or scenario was it doing better. Is there a logic between certain algorithms doing better in a certain subset of your data? Is there a reason why that's happening? Like, in a data set where the number of features is not that much, is not that large, you might all of a sudden realize that, hey, kernel-based approaches are doing much better across all the experiments. So that's an interesting sort of conclusion, and it'd be interesting to be able to maybe generate some reasons as to why that is happening. So this is where you might be slightly touching on areas such as interpretability and explainability of AI, right? Where you try to explain why something is happening, right? So that would be nice, instead of just popping a table of results, to be able to actually accompany that with some sort of explanation as to why this is happening. And the second pointer so this was number 1, right? This was number 1. The second thing that would be really good if you could have is called statistical test. We have a variety of statistical tests out there. You have t-test, you have like student t-test, ANOVA test, and many, many more, right? Each one is appropriate for a given scenario, for something. But my point is, whichever suits your scenario, you have to pick that one. But it's important to have them, because if you say that, look, one class SVM is the winner, a statistical test would tell you what are the chances of that having happened but purely by chance, if that makes sense, right? So is it really better or not? So using a statistical test, you could actually say, look, with probability of 98%, this hasn't happened by chance. There's actually certain inherently stronger for one class SVM compared to the other algorithms that has made one class SVMs better in these experiments, or have proven them to be stronger, right? So using a statistical test, especially when the application is, I'm addressing those of you in particular who are actually working in projects where the outcome of your code, of your implementation, is going to be something that's going to be used in medical data and making decisions about patient records, right? Here, a statistical test could actually determine what are the chances of this, say, decision about this patient being, correct purely by chance or not, right? So in particular, in sensitive applications, using statistical tests would give you a degree of assurance, comfort, in terms of how trustworthy my algorithm is for this in this scenario, in this experiment. Okay, and you have to make sure that you choose the right one. Okay, great. I think I'm done with everything that I want to talk about. It's been nearly 2 hours, but I hope that this has been helpful. This has been useful. So let me bring myself in the middle. Okay. Okay, folks. It was long. I'm sure it was exhausting for you guys, and I hope that during that exhaustion, that interminable video, I hope that there were sort of interludes of enjoying the content as well. So, just as a short summary, right? I'm just gonna go over everything very fast, right? First of all, in order to create a machine learning experiment, number one, is the problem I want to tackle interesting? Do people care about solving a problem like that? How people have been solving it in the literature? What kind of methods have they been using? Next, do I have data? Have I checked out the websites, the website of the creators of the datasets in terms of me being able to use those data, right? Am I allowed to use it? What are the terms? Do I need to apply for something, some sort of form? Do I need to take a course or something? Do I need machine learning, or are there other simple techniques that could actually solve the problem? Have I gotten comfortable with my data? Looking at missing values, looking at class imbalancedness, looking at outliers, looking at some visualizations about the distribution in my data. Have I defined the task at hand? Is it going to be supervised, unsupervised, semi-supervised, reinforcement learning sort of approach? Is it going to be classification, regression, forecasting, and so on and so forth? Have I chosen a good selection of machine learning algorithms as my benchmarks that are reasonably different from one another, just so you could cover a good variety of families of machine learning algorithms out there, from simple all the way to difficult, sophisticated, overly parameterized models, let's say. Have I defined my hyperparameters for each algorithm? Have I defined the right method of fine-tuning those hyperparameters? What optimizer am I going to be using? How have I divided my train, validation, and test sets? Am I going to be using 10-fold cross-validation, 5-fold cross-validation, 5 times 2 cross-validation to add iterations? Have I used the right evaluation metric? Am I reporting the right values, which should be the values on the test set? Have I made sure that I have never, ever, ever, ever looked at my test set? And it's going to happen to you, by the way. Trust me, it has happened to everybody I know, including myself. But at some point in your research, your test set will for sure leak into your training set. So be careful not to do it, but it will happen. It's sort of an inevitability that's going to happen to everybody. It's one of those lessons that need to be learned that way, the hard way. So provide some insight into the results of your experiments, why something is happening, why is this algorithm doing better, in which scenarios and what data is this algorithm doing better. Can I shed some light as to why this is happening? And the last bit, use a statistical test method that could actually help you determine the chances of your results having happened purely by chance or based on some inherent ability of the network or your algorithm, right? Okay, I hope that this has been informative, folks. I'm gonna end the stream. I hope that if I ended the stream, it would actually save the video. I mean, the last time I did live streaming was long ago, so please God, it will actually save this. So I presume if I just clicked on end stream, it should save it. Anyway, so before I go, thanks a lot to all of you for watching, and thanks a lot for all of you who were here during the live session, and to all of you who are actually watching this after the actual live session. So I'm gonna be ending the stream. So stream. So on behalf of Amal Don, take good care of yourselves and best of luck with your machine learning journey. Bye.